Hello, Mr. Thomas. I am doing this on the day it's due. So, I am dedicated. So, this is the Stellar Cycle with Carlo Johnson, because I'm super cool. And yeah, let's get started. So, first, we gotta understand what makes a star, and that is fusion, nuclear fusion. Basically, this is where two elements combine to create a new element plus a little bit of excess trash. Well, I don't know if you would call it trash. Like, usually it could be neutrinos, gamma radiation, all of this stuff. And there's basically two main forms of fusion that happens in stars. Lower mass stars usually tend to have hydrogen fusion, or what is known as a proton-proton chain. These are stars like our sun, who are right now fusing a bunch of hydrogen molecules and then producing more and more hydrogen molecules to then produce helium. These stars don't need as much energy to use hydrogen fusion, so they have really long evolution spans. Compare that to the CNO cycle, which uses obviously carbon, nitrogen, and oxygen, and this requires so much more energy that their evolution span, which when I'm talking about evolution span is basically their lifespan. Their evolution span is so much shorter than the stars using fusion or proton-proton chain. So much so that you can see stars using the hydrogen fusion that live for billions and billions of years. And if you see a really big star that uses CNO cycle, unfortunately, it doesn't live as long, only couple million of years sometimes. And then we have to know what stars are. So we're going to talk really quickly before we even get to even the stellar cycle about stellar classification, or I like to call it stellar classification. So basically, stellar classification is how we categorize stars. There's different ways to categorize different stars. And there's two main ways to categorize the stars. One of them is spectral classes. And before I even say anything about spectral class, the two ways to identify stars is temperature and size. Those are the two main things that you need, maybe a little bit more, but those are the two main things. And spectral class tells us the temperature. Now, to the right here, you can see the spectral types not only also give us the temperature, but also the color of the stars. Now, a good way to remember this order is all big ass fat gorilla kicked me. Yeah. Or if you want to include this extra one at the bottom is all big ass fat gorilla kicked my cat. And it could also be S down there, but this particular graph that I came across only has cat, so no cat Steve. The hottest stars are going to be the ones up here. They go up to temperatures of 25,000 kelvins, really, really hot. And all the way down here, you can see stars as low as 3,500 Kelvin. So the difference is big. There's also a 0 to 9 number thing where it tells you the hotter the star of that type. So for example, an O0 star is the hottest. It goes from lowest to highest, and the lowest is the hotter, and 9 is the coolest. So O0 stars are the coolest. The hottest stars, while O9 stars are the coolest, hottest stars. The coolest stars you'll see are probably M9 stars. But then O0 stars are the hottest by far. And then you have luminosity class, which tells us another important thing: size. This is organized in Roman numerals, and these main ones up until the Roman numeral 5 are called main sequence. We'll explain that later. But then these two at the bottom, subdwarfs and white dwarfs, basically are not main sequence stars, and we'll explain the difference between what these two are. But these mainly tells us the size of the stars. Like, stars are the biggest stars, and they're extremely big. And then we have supergiants, supergiants 1A, supergiants 1B, and then it goes 2, 3, 4, 5. And those are the spectral class. Now, a good example of how to classify a star is we'll classify our sun. So you see, our sun is a yellow star, meaning it's G. It is a dwarf, meaning it is a main sequence 5-star, and then it's a G2 star, meaning it's around 5,000 kelvins. You know, we have a pretty okay star. It's a dwarf, but it's a pretty okay star. Moving on, how do our stars birth? Stars are birthed from a planetary nebula, where there's a bunch of gas, and the gas basically gets attracted to one another via universal gravitation, and gravity just clumps it all together, clump, 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 boom. You have a star, and that's where it creates nuclear fusion. This is one of the famous planetary nebulas. It's called the Pillars of Creation. You know, Pillars of Creation, and basically this is, and before and after that there's a little phase called a protostar, and this is an illustration of a protostar actually by a great artist. I don't know his name, but basically they're 100 light years across, and they contain 6 solar masses. This is basically like a baby star, and this is where stars will be born, and then you have the star. So then we get into the main sequence, which is where most of the star will be in its lifespan, in its evolution span. Excuse me. Don't say lifespan around Mr. Thomas. He will not like that. Most stars will spend their lifetime in this phase. The stars in the main sequence are very healthy, stable stars, and they will spend billions and millions of years just either using the CNO cycle or the hydrogen fusion. And then after a while, they will go into the red giant phase for lower mass stars and higher mass stars, and eventually the higher mass stars and the lower mass stars will diverge in paths. You'll see eventually. Our sun is right now in the main sequence, while this star right here, one of my favorites, Betelgeuse, is not a main sequence star. It is actually in its red giant phase. So this is where Betelgeuse lands, and this is when a low mass star runs out of hydrogen fusion, or the CNO cycle runs out of some kind of fuel. And basically, they both move from fusing hydrogen or fusing CNO to fusing helium, actually, and all the excess helium is now getting fused instead of the hydrogen, and this creates like an exponential growth in the star's size. And you see how much bigger the star gets over a span of just a couple million years. Our sun is going to reach this stage in approximately 5 billion years. So so unless you are immortal, you do not have to look forward to that. Then you get into the actually we're going to go like this. So first you go into the horizontal branch, and that's basically when it reaches the tippy top of the red giant branch, and then it goes across, right? So basically, this occurs right after the red giant phase, after a bunch of helium fusion kind of created an explosion. This is one of the final stages of low mass stars, and eventually after this will become a planetary nebula, where it becomes a planetary nebula, and planetary nebulas create stars. And so basically you just saw how a star recycled itself back into more stars. It's actually kind of fun. But then after that is the isotonic giant phase. Basically, this is the last phase of burning. Burn. They're just burning the rest of the fuel they have left. And after this, they will eventually become either a white dwarf neutron star or a black hole. Super, ultra, duper cool. And that's my favorite star series. Basically, the difference between the supermassive stars and the lower mass stars is a bigger star will have an extra phase called the supermassive supernova, or just a supernovae. if you really want to get technical with it. I call it supernova. You can call it supernova. It depends on your preference. Basically, low mass stars cannot do this because they don't have enough energy, but big mass stars have all this energy kept up, and then boom, they create a supernova remnant, and this is Cassiopeia A, which is a remnant of a supernova actually. This is an explosion, and eventually the explosion will succeed and all that, and eventually these supernova remnants will become two things: a white dwarf, no, not a white dwarf, excuse me, that is a neutron star, or a black hole, super duper cool. So these are the different stages after a star's life. So first you have white and black dwarfs. This is going to happen to our sun. Our sun is going to become a white dwarf. This is basically just a big helium ball essentially. And a white dwarf is the size of our sun actually. And basically it's not healthy. It's basically dead. It still has some fusion in it. And it's very highly dense. It's heavier than our sun, but it's the same size of the sun. Let that sink in a little bit. Now this is a neutron star. Now this is where it really gets crazy. This happens after a supermassive star, didn't become a black hole, but then it became a neutron star. It's basically doing this thing where it's fusing neutrons, which is like super ultra cool because it's not really common, where neutrons fuse. And it's also pure neutral, so it's really one of the only things that is actually truly neutral in charged particles things. But it's really dense. It's the size of Rhode Island, but it's heavier than the white dwarf, which is heavier than our sun, which is honestly insane. But if neutron stars, or the star in general, was super ultra duper big, it becomes a black hole, which it's not like in the movies, unfortunately, where it absorbs everything. It has this short shield radius around it where that's where you're safe to be, but then as soon as you cross it, there's no going back. There's not much known about black holes because they're still kind of new to us, and we're still trying to learn them. But as soon as you cross, you can't really come back unless you're like literally going at the speed of light. There's no coming back. So that's probably where my dad was saying, because I've never seen them since last year. And thank you for watching, and to show you a supernatural, super ultra mega supernova explosion to end it off.